Well, welcome back to a discussion. It'll be a little bit different today. Usually we've been involved with all the stages of solving scientific problems, computing, math, and science. And today we'll do something a little bit different. We'll step back. We'll talk about high-performance computing hardware, memory, and CPU. Not to worry. Some of you are probably recoiling already at the thought, oh my gosh, this guy must be a number head, a hardware person. We're going to learn about all these things I never wanted to learn about. And that's fine. Don't worry about that. What we'll do is we'll try to look inside a computer at the kind of knowledge a scientist should have when they use a computer to do science. Okay? The point of this whole thing is insight, not numbers. So we want to understand what a computer is doing. The numbers I could tell you right now, how fast this part of the computer is, how fast that part, it's going to be out of date, in a week or two probably. But the general trend, that's what you want to take away. Also, something that's a little bit different in this lecture than previously is we'll talk about high-performance computing. And high-performance computing sometimes is like supercomputing. It means for scientists to use computers to do forefront work, to use computers to solve problems which are very important to society, that tend to be big problems, complex problems, to solve problems that couldn't be solved otherwise. So we're not just using computers to help you solve a homework problem in physics. There's nothing wrong with that. But now we're saying, if I want to make a change in the world, if I want to face some of the grand challenges science and engineering has, I have to use computers at their limits. And then you need to know some of the tools. So that's the second part of what we want to do. We want to understand what goes on inside a computer, then we want to say, how do we use this to solve really big problems? Okay. So here on slide 2, we talk about the basic problem that we face. If you have a real big program, we want to optimize it for speed up. In other words, we want it to go fast, as it normally does, but then make it go even faster. Okay? Well, there's several ways to do that. The rule of thumb for practical people is the best way to make a program go faster is by you being smarter. In other words, don't go around looking for the biggest iron, in other words, the biggest computer you can find. Go instead, inside your program, look at the algorithm. Think if there could be a better algorithm or more clever way. Often you can get a much bigger speed up that way with much less work than you can by changing your program to run on some architecture, so forth. So the practical rule is, if you can avoid doing it by being smarter, don't do it. Okay? But then, if you're doing high-performance computing at the limit, so if you're solving a very, very big problem, if you've used the limit of all the computing power you have and you still can't get the program done fast enough to solve your needs, then you need to tune the program to a computer's architecture. So architecture is how the computer is set up, how it works internally, how it actually processes numbers. And tuning it means speeding it up. It means, as we see here, it means looking at your program and looking at the parts of it here where its computer spends the most time. So those parts are called hotspots. Okay? And it makes no sense to try to make the program run faster in the parts where it doesn't spend much time. The biggest bang for the buck, the most speed up you can get, is to speed up the parts of the program where the program spends the most time. That's where you should focus. So you have to do that first to speed up a program. There's a negative side to optimizing programs. And this is a controversial topic. We'll talk about that some more. Computer scientists don't all agree. Scientists don't all agree. To optimize a program requires lots of hard work. You don't mind that if it was the computer's hard work, but it's going to be your hard work and your time. This is very intensive. If you have a real big working program, a research code, and you try to optimize it, or you try to run it on a big parallel machine, that may often take weeks, months, even a year's time or more. These can be very complicated issues. So you want to keep it as simple as you can. And the other negative part is that once you get the program optimized, you get it optimized by making it work on the local computer as best as possible, and then you end up with programs that are not as portable as they used to be. They might be, faster, but you can't take them to another computer and expect them to work as quickly or work at all. You may have to change them for that computer as well, and you also end up with programs that are less readable. You've had to do things, we'll give examples, to make them run faster, and they do run faster, but they don't look as nice. So you pay a price. Okay. One point of view is that of a straight-line computer scientist who say, it is our job to make programs run fast. You keep hands off. Don't go here. Okay? We'll keep writing better and better compilers to do the job for you. You shouldn't get involved with that. And that is a good goal. It certainly may be the way things go. They haven't in the past. So many computer scientists say stay away, but computational scientists will say, wait, I have this large, very complex program. I'm running it all the time, and I can get a speed up of 3 to 5, maybe 10 by just tuning it, even though the compiler is good. And if I have to wait around 8 hours to get my results, and instead now I can tune it and get my results in an hour or two, I can get 2 or 3 times as much work done, and that's very important. Okay. Finally, to give you some enjoyment of the kind of controversy that goes on in the different communities, Press, who's had one of the most influential books on the subject matter, has a quip in it and says, computational scientists solve tomorrow's problems with yesterday's hardware. Computer scientists seem to do it the other way around. You should look at that. So let's now move on to slide 3. So slide 3 gives you one view of the theory of how to optimize a program to get it running. So I will read the slide to you, and we'll go through 9 different rules. Okay, and these are not any one rules that I've put together. These are rules put up by people with wisdom developed from years of hard work, from years of observation, and they'll give you various perspectives. The first rule: more computing sins are committed in the name of efficiency without necessarily achieving it than for any other single reason, including blind stupidity. In other words, you can cause a lot of trouble by trying to make your program run well. You know, as the farmers would say, if it ain't broke, don't fix it. Okay. One of the leaders of computer science have said, we should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil. Okay. So this says, by and large, don't worry about optimization unless you need to. You can get into more trouble than not. Voltaire, the best is the enemy of the good. If you have a very nice program which is meeting your needs, and you say, let's try to make it really perfect, make it more efficient, you can do a lot of harm. Okay. Expert wisdom, do not do it. It's a lot of trouble. Okay. For experts only, if you want to do it, do not do it yet. Put it off till you're forced to. How will you know when you're forced to? You'll know, because if you're threatened to lose your job or have someone else get the grant because you can't get your work out fast enough, then you may want to do that. Do not optimize as you go. This means don't worry about something being faster or getting something to be faster when you're writing the program. Concentrate on getting the mathematics right. Concentrate on getting the algorithm right. Concentrating on it having give good results. Don't worry about figuring out how to make it faster. The next rule, number 7, which is probably one of my favorite because it seems to apply to everything, but very true here, is remember the 80-20 rule. This is also known as the 90-10 rule. And it says you can get about 80% of the results usually with about 20% of the effort. So if you can write the program well, tune it up a little bit, you get very good results. Trying to get even better results takes a huge effort with very little return. So finally, we get to some very important rules. 8. Always run before and after benchmarks. This means a number of things. Number 1, once you need to know if your program is really being sped up or if you just feel it's being sped up. Number 2, you need to make sure that you get the same answers. Either you or the compiler itself, if you tell the compiler to speed things up, can speed things up, but sometimes give you the wrong answers. And recall, we're doing science here, and having the wrong answers fast is not worthwhile. I mean, what we're trying to do as scientists or engineers is either search for the truth or build bridges which don't fall down. Getting the answer faster when it's not the truth or when the bridges aren't safe is not worthwhile. I have to admit at this point, I once stopped a workshop I was at when the leader of the workshop explained to scientists how they put too many synchronization marks in their code to run in parallel, and it slows the code down, and they should remove these to get faster running code. And I objected, saying, no, those are put in so you know you're running with the right data at the right time. And he thought, well, yeah, but then you won't get the research grants. You won't win any prizes for being fast. So this is a case in point. Being fast and having the wrong answer is wrong. Finally, the most important rule: use the right algorithms and data structures. Use good programming practices. That's almost always the best way to optimize. Okay, so now let's get away from the words and let's look at something real that goes on. So, slide number 4. What are supercomputers? What's a high-performance computer? So if you look at this slide, you see a little picture there, and we'll talk about that picture in detail shortly, but that's an example. At this instant of time, maybe last summer, that was the world's fastest computer configuration which existed. What's a supercomputer? It's hard to handle and get a handle on that one. We could say the supercomputer is always the fastest, most powerful computer that's around. There's different ways of doing it. They changes with time. Now, supercomputers are almost always parallel machines based on personal computers, PCs, or workstations, WCs. Okay? So they're, in a sense, non-proprietary hardware and software put together massively to run fast. In years past, you probably heard of the Craze computers. Those were proprietary. IBM had some also. They would design their own hardware and software just to make a very fast computer. Those machines are almost all gone, but not all. Okay? So as we said, most supercomputers today are massive collections of PCs, workstations, whatever. They tend to run Linux or Unix, which is a good thing. Imagine how many hundreds or millions of dollars we'd have to pay to Microsoft for contract licenses if we used Windows on a 30,000 node computer. Okay. What makes a high-performance computer good for science, what makes really a supercomputer, is that it's not just the fastest components you can buy, but it's a blend. It's a good balance between all the major components. And as we'll see when we talk about the details shortly, you don't just boost every component up to the major speed. Everything has to be balanced. And the first item is multi-stage pipelined units. And we'll talk about that in detail, but that's getting into the architecture. The way the central processing unit, the CPU, is assembled has multiple stages. So this is like a fire brigade. You have information coming in, buckets of data coming along, and those are the pipelines. They're always coming in, and multi-stages. The CPU and the software are looking ahead, figuring out what has to be done, and has those stages getting ready even though it's not their time yet. So that's what multi-staging is about. Generally, multiple CPUs. On parallel machines, that's obvious. You have lots of CPUs. But even on ordinary machines, they'll have various elements of the CPU that run in parallel to do simultaneous activities. You have to have that to work fast. Fast central processing unit is very important, but it must be compatible with the rest. So if you just go on the internet, the web, you go shopping, you look to buy the fastest CPU, it may be faster than what you'll find on the world's fastest supercomputer, but it won't give you a particularly good computer. It's just a selling point. What is important, particularly for science and engineering, is we have to have very large and very fast memories. We deal with big data structures, we deal with real-world problems, and you have to have lots of memory to get to that, and you have to get to it fast and get to it very well and accurately. Finally here, the communications amongst all the parts must be very fast. What we mean by very fast is faster than the slow parts, as fast as needed. Faster the better. Vector and array processors are pieces of hardware which analyze an entire vector, which is computer science term meaning an array, a matrix, in one fell swoop with one command. This is a little controversial. They used to be the bread and butter of supercomputers. Now very few manufacturers include vector or array processors in them. Some do. Some popular gaming machines, some popular personal computers have vector processors just to speed up the graphics cards. Okay? So they're there, but you usually don't program for them directly anymore, except if you're on a few machines. But some people say they may make a comeback. So we have to see. Finally, the last major component of a high-performance computer is software, which integrates all of this together very well. My own personal view in the last decade has been that software has been ignored or forgotten by the supercomputer manufacturers. These computers have moved along, their power has gone so fast, but the software to run them, particularly for scientists, has not kept up. So you yourself have to know now more about them than you might want to, that I want to probably, just to be able to use them. Let's hope in the future that changes. So now let's get into the nitty-gritty. Take a look, strain your eyes at this next slide, slide 5. What should we say? Before we get started, we should probably say that if you're doing high-performance computing, you're probably dealing with mathematical matrices or vectors, or what computer scientists will call arrays. Okay, so array is how we store them. The mathematical form will be as a vector or as a matrix. In other words, you wouldn't be doing a very big problem unless you had huge amounts of data, huge amounts of information, huge amount of calculations you had to go through, and you usually use matrices to organize this. So high-performance computing almost always deals with matrices, hard as it is to believe. That's why having a vector processor, which just deals with matrices, is so important. If you're just dealing with random numbers and not matrices, then some of this doesn't matter in the same way. And there's lots of computing, much of the biological computing, that does that. So let's talk about how memory hierarchy affects computers and what we mean by memory hierarchy. So on the left of slide 5 here, you see an idealized view of a central processing unit. And we'd like to say, aha, in memory here on the left, we have a vector A with elements from A1, A2, A3, up to A sub n. So capital N is the length of the total vector. And we say that's in memory, the CPU can get to any element at once. And then there's a vector, after the vector there's a matrix M, and it has elements 1, 1, 2, 1, 3, 1, etc., all the way down to NN. So even in this ideal world, notice that the matrix here is stored in a linear form. In a more ideal mindset, it might be stored as an actual matrix with rows and columns like you use them mathematically, but it's always in some linear form, or at least easiest to keep track of that way. That's fine. In the real world, matrices are not stored as one block in the computer unless they're small matrices. And if you're dealing with that smaller problem, you don't care about high-performance computing. So when you're dealing with matrices with maybe several million elements, you're not going to put them all in memory at one time, particularly if you deal with hundreds of these matrices. So what you might have here, and now we get on to this hierarchy business. What we might have here is memory here on the left being what kind of memory? It's not RAM, so this would be on the hard disk, your files where you store the information. Down below here on the right, we have the central processing unit with registers, which is just little bits of memory where we'll actually do the processing. So how do we get from the hard disk on the left to the central processing unit on the right? And the answer is in a number of steps. Okay, so first we have RAM, random access memory. So this is the fast memory, the central memory on a computer that can be accessed randomly by the central processing unit. So it can get to any piece of it at once. But when you say, let me store matrix M in memory, let me store vector A in RAM, it all doesn't get stored. What gets stored is a page at a time. So the computer will read in a chunk or a page of that vector, put it into RAM, for example, page 1. It'll then read another chunk of, let's say, the matrix M, put it in page 2, and another chunk, put it in page 3. So have separate pages, and the sizes depend on the details. And then the rest of this matrix, which the compiler may have figured out it is used at some point, it may be around in swap space waiting to get into RAM as well, which is just another cache, sort of buffers. Then when these pages are needed, they're fed in individual elements of them into data cache. So this is a bit of high-speed memory, very high-speed memory, that feeds the CPU. Okay, and so that's how it works. You've probably already noticed on the left that I've said everything is in linear order, and that's true. And there's another complication here, which is not really a problem. You may think it is, but in Java and C, matrices are stored in row major order. So row major order is the way you might, think. If I have a matrix, I just go, I go through row 1, M00, M01, etc., till I get to the end of the row. Then I start row 2, M10, M11, until that's done, M12, and then so forth. That's how C and Java do it, row by row. Fortran stores it in column major order, which is stores the column down, down. So you see M11 followed by M21, so it's going down the columns. Either of them work equally well. No one is inherently better than the other. They both have the same kind of problems. One problem being the diagonal element in row major order, M00 and M11, are quite separate from each other. And beginning in 0 is just how things are done in C and Java. Beginning in 1 is the usual Fortran convention. And in Fortran, M11 and M22 are also stored apart from each other. So there's no obvious advantage to both. Whatever you want, you use. Okay, so now we've already given you some specifics, and now let's talk about why we call this thing memory hierarchy. I know that was sort of confusing on the last slide because there's a lot of details already. We'll come back to that. You'll see those pieces and how they're used, and let's talk about these memory hierarchies. So what we have here on the right, we have our pyramid. And at the top of the pyramid is the CPU. And if you look at this pyramid, you can think of it in a number of different ways. Okay? Well, it's multidimensional, right? It's a pyramid, it's not a triangle. In some sense, the base, the bottom, is the largest amount of storage. And then at the top, the CPU is the smallest amount of storage. And you may say, why is this guy calling the CPU storage? Well, because that's what it is. Most of the CPUs, it's just memory. It's just very, very, very fast memory. And so what you have here is, on the bottom, the main storage is also the slowest memory. So in time, this is slow. As we move up, we have different kinds of memory, and each kind goes faster. So what we have here, main storage, and on the right-hand side of this pyramid are some numbers. These numbers change every time I revise this slide, and they always go up, okay? So the numbers don't matter so much. They're useful, and they're useful in their relative proportions more than anything else. So that's sort of the wisdom you need to carry away, The relative sizes here matter. So main storage, huge amounts, 32 terabytes, okay? So tera is 10 to the 12th. Okay, it's a huge amount of data, and it's being transferred back and forth right now at about 111 megabytes per second. Okay, so it's a huge amount. It's slow by CPU standards, but it's fast otherwise. The main storage doesn't go directly into RAM, as we've seen on the previous slide. There's this cache. So cache is a buffer. It's fast memory, and in this case, it's 2 megabytes of it, so there's not that much of it, so the program has to know ahead what's going to be used and move it through cache fast, and the cache is fast. Then you get to random access memory, could be 2 gigabytes, typical number. That's very fast memory. Then cache, another cache, a different cache, feeds the central processing unit. So the central processing unit here is getting fed at like 6 gigabytes per second, which is very fast. If you compare that to 100 megabytes per second, we see that there's easily a factor of 10 or more in speed. So as you go up here, the speed is going, getting faster by a factor of 10. Notice though that the amount of cache, this very high speed cache at the very top of the memory hierarchy, is very small. There's only 32 kilobytes. Okay? So, when we speak about cache, at the top, we're speaking about high-speed buffers. Buffers being something with like shock absorbers that keep things moving more smoothly. 5, 6 gigabytes per second is fast. But when you're dealing with cache, you're always dealing with latency issues. It'd be nice to say, I will just move a piece of data from RAM to CPU via cache. You can say that, but you know, just like your sleepy dog in the corner, it doesn't jump up and react immediately. The computer doesn't jump up immediately and do what you say. There's latency. It takes time to get the data from here to there, to move it along. Those are things you have to worry about. Okay. One of the major developments in scientific computing, and now it's come into the gaming world as well, and to popular computing, is RISC. And we'll talk about that in detail, and that's reduced instruction set computing. Excuse me. So all of these computers that deal with cache a lot, that deal with data flow, and really concern themselves with how to program data flow most efficiently, they came about from this RISC philosophy where that was very important to do, and that's how you speed up the computer. Okay. So as we've seen here, the hard disk is very slow, but it's very cheap. That's why there could be so much of it. And in years past, some like Cray supercomputers would say, really, this is very complicated. Do I have to do this, have caches, different kinds of memory? And the answer is no. If you want to spend all the money you can get, you can build a computer in which the CPU is the same speed as the cache as the RAM, and you just do away with caches entirely. Make everything very fast. It works very well. It's smooth. It's easy to use. The only problem is it's expensive, and not enough people buy them to keep them going, so now we have to put up with this. Okay. Pages. Remember we talked about memory not going in word at a time, but the computer looks at the whole area surrounding the word you might want and say, if this guy wants this one word, he probably wants other stuff as well, and moves the whole page into memory. On 386 type processors, Windows type Intel machines, usually the page length is something like 4K. On Unix machines, it varies from 8 to 16K, so it's a little bit bigger. But that's not gigantic. Okay? And if you think if you have a matrix with 1 million elements, you can't get even a big fraction of that in memory at one time, so that's why we have a concern. Finally, there's virtual memory. And virtual memory was a blessing back when I was a grad student and computer memories were ridiculously small, and we had to worry about programming everything to fit into 16K words memory or 32K word memory, and that was very hard. And then this idea came out that, wait, view memory as if it's infinite, and then if the word doesn't fit in memory, the computer will just automatically swap it in. So it's like virtual memory, and virtual memory is just about infinite. Today, on a 32-bit machine, there's about 4 gigabytes of virtual memory. And that's, you know, that's a huge amount. It's very inexpensive to use, very little effort on your time to use. It's very expensive on computing time. And as we'll see with demonstrations, there's often an order of magnitude, a factor of 10 increase in running time if you run into what's known as page faults. In other words, if because you've said I want some piece of memory, some word that's not yet in memory, and the computer has to switch pages around, that's called a page fault. That could take about 10 times as long. Yeah. But you use virtual memory all the time, and you love it, and you may not realize it. So in multitasking, which used to occur on Windows rarely, but mainly on Unix machines, but now also on Windows and Macs, when you have lots of jobs running at one time, or you have lots of windows open at one time, what's happening when you have many windows open at one time is you have memory here, and you have the programs residing in different parts of RAM. And of course they all don't reside. They look like they do because they're using virtual memory. And that's only possible because of virtual memory. So sometimes when you're at your computer desk and you're working on one window and you click another window and you say, over here, I want that to work, you notice a delay. And you say, why is it delaying now? It was fast before. Well, that delay is because you may think that program is running, but a lot of it is in virtual memory. It has to get reloaded, and that's why there's a delay. Well, that was a good amount of material we've already covered. We have some more to cover where we'll give examples, but probably this is a good time for you to take a break. For the more industrious of you, maybe just to go back and look at the material again, make sure you understand the rules and the words, because after all, Landau's first rule is just learning the words is what education's all about, and we've had a lot of words so far. So let's do that. Let's take a break. Then we'll come back and give some examples of how these ideas are implemented.